This is part 1 of lecture 4. We will continue our discussion on neural network, and we will talk about some smaller problems like how to speed up and how to improve gradient descent, and also how to adapt how to adapt neural network to solve problems with multiple classes, and so on. So it will be less mathematical, of course, compared to the last lecture. So the first thing I want to talk about is, many people noticed this already, is when we are training LTU perceptrons using the perceptron algorithm, we are updating the weights once after each instance. Reminder, instance means a sample in the training set. So we are updating the weights after each one of them. However, in logistic regression, we are updating the weights after summing up basically the gradient over all the instances. So the reason this is happening is because in the perceptron algorithm, this is not a gradient. We are technically not mathematically minimizing something. We are just using some kind of geometric hack that works. So it's not gradient, so we can do whatever we want. But this is gradient. So when we take the gradient of C, the cost with respect to the weights, we get the sum as part of the chain rule. So we cannot just use one part of this gradient because it will no longer be the derivative of the cost. So we do not want to arbitrarily separate the sum. And the question now is, can we actually do this for logistic regression? And more importantly, can we do this for neural network? Because each one is very hard to calculate for neural network. And the answer is yes. And it even has a very fancy name. It's called stochastic gradient descent. So when people say stochastic gradient descent, what they mean is basically just pick one instance randomly each time and compute the gradient based on that one instance. And then we update the weights. So the reason why it's stochastic is because we are picking the instances randomly. So when we pick many random instances, on average, the gradient based on one instance will be equal to the gradient based on all instances. So that's why we're calling it stochastic gradient descent. And there is a variant called mini-batch gradient descent. I think you can guess what it is. It's just a small subset of instances, and we sum it up, and it's called mini-batch gradient descent. So one common misconception is what we're doing is this. So in gradient descent, we are making like a huge step towards the minimum of the cost. And in stochastic gradient descent, we're just like taking tiny steps. And if we sum these things up, we will get to the same place. And from the formula, it looks like it, right? So it looks like sum of these n steps, n is the number of sample points, it is equal to that. And this obviously is wrong. If this is the case, well, why are we doing this at all? Because like we go through the training data once, and then we arrive at the same place, right? So this idea is wrong. Let me actually draw the correct one. So the actual gradient descent step, it could be large, but suppose it's this large. And stochastic gradient descent is not small. It's not each step is small. The step size is controlled by the learning rate, not by separating the gradient. So each step is random. So what it means is the random step may be the wrong step. So for example, the first step may go here based on our first instance, and second step may go here, and there may be correct steps, and there may be like completely wrong steps. But on average, these things should be correct. So a more accurate diagram would be something like this. So if we go through the training set once, actually stochastic gradient descent will go further compared to regular gradient descent, going through all training instances once. So this is the end of the model as well. So the logic behind this is computing the gradient for all the instances based on the same initial set of weights, and this is computing just one of them based on the initial weight, and computing the next one based on a better, maybe improved weight. And here it's even better, because what I mean by better is closer to the minimum here. So each step we are calculating the gradient based on a better set of weights. So of course, when we add them up, the end result will be closer to the minimum. So let me write it down mathematically as well, in case you want to see that. So for regular gradient descent, we are differentiating the cost of, say, the first instance with respect to W based on our bad guess. So remember, the initial one is really bad. It's just a random guess. And we're adding up the second instance cost, the derivative based on the same bad one. And we're adding the third one based on another bad one, and so on. In stochastic gradient descent, okay, this is bad. Stochastic gradient descent, we're computing the derivative based on the bad one only once for the first instance, and for the second instance, we already updated from 0 to 1, so this is slightly better, and we're computing the gradient at this better point, so more or less the gradient will be better as well. And similarly, I think I'm indexing these incorrectly. So that one is even better. So that's why in general, if we go through this training data once, stochastic gradient descent will actually get further compared to regular gradient descent. That's why you should use this. And the next two slides are just summaries. So we are calculating gradient now only based on an instance I, so I should have i's here, or if I don't have I, these should be approximately equal. And one important thing I actually want to mention is that the way that we usually do this, instead of just randomly pick one instance, because you may like pick the same instance more than once and never pick some of the instances, so that's not good. What we usually do is we randomly shuffle the training set, and we just pick the instances in order of the permutation. So that is also what you are recommended to do for programming homework 1. And this is exactly the same step, so I'll not spend time talking about this. One thing I do want to talk about is how to choose alpha. So the choice of learning rate, last year I did not talk about how to use varying learning rate, and it seems fine, but may not be great to always use a constant learning rate, because as you saw in the gradient descent demo that I showed you in lecture 2, when it gets closer to the minimum, we should decrease the step size. So if we are already very close to the optimal weights, we should not update a lot. I mean, based on the gradient. So one popular choice is the square root rate of decrease of learning rate. So we still start with alpha, and in the first iteration it's just alpha. In the second iteration we use alpha over square root 2, and in the third we use alpha over square root 3, and so on. So that's one very popular way of choosing learning rates. And people also do this in some cases. I personally recommend this. And for the homework, you may want to choose alpha to be like a quarter and try if something like this would work. And of course, there are more sophisticated ways of choosing step size. So the first group of things we can do is we can use second derivative information, because we can actually analytically compute the second derivatives. So we can use that. So I think most of you know Newton's method, which is just calculating the second derivative every time. And a approximation to Newton's method is called BFGS, which is very commonly used in training neural networks. But you are not required to learn this. It's very complicated mathematically. And there are also some adaptive method, which means we're not only based on the number of iterations, we're also computing the learning rate based on the gradient in the previous steps. So some of the popular method is ADA grad, adaptive gradient basically, and ADAM, I think is adaptive moment estimation or something similar to that. So if you are interested, you can look into these. And I think they are relatively harder to implement, so you are not required to do this for the programming assignments.